Everything you were taught about your place in space is wrong. You're not standing still, not even close. Right now, as you watch this, you're spinning with the Earth at over 1,000 miles an hour. You're hurtling around the Sun at 67,000. And the Sun itself, the one thing we point to as the fixed center of it all, is racing through the Milky Way at more than 500,000 miles an hour, dragging you, me, and every person who's ever lived along with it. And that's still not the real number. Stick with me, because by the end of this video, you'll find out just how fast you're actually moving through the universe, and it's a speed almost nobody knows. If you're new here, this is exactly the kind of question we chase down every week. So hit subscribe before we dive in. So let's start with the ground beneath your feet, because even that isn't as solid as it feels. Right now, you're standing on a planet that's spinning at roughly 1,000 miles an hour at the equator, a little slower the farther you get toward the poles. You don't feel it, because everything around you, the air, the buildings, your coffee cup is spinning right along with you. It's the same reason you don't feel like you're moving when you're cruising at altitude in an airplane. Galileo figured this out nearly 400 years ago, and it's still the best way to understand why a rotating, orbiting, hurtling planet can feel like it's standing perfectly still. But rotation is just the beginning. While Earth spins on its axis once a day, it's also racing around the Sun at about 67,000 miles an hour. That's fast enough to cross the entire continental United States in about 4 minutes. And here's the part most of us never think about. That orbit isn't a perfect circle. It's an ellipse, slightly stretched, with the Sun sitting off-center at one of its two foci. In early January, Earth swings closest to the Sun, a point called perihelion. In early July, it swings farthest away, at aphelion. If you've ever wondered why the Northern Hemisphere's summer isn't actually when Earth is closest to the Sun, that's your answer. It's the tilt of our axis that drives the seasons, not our distance from the star we orbit. Now picture the solar system the way it's usually drawn: the Sun sitting dead center, planets tracing perfect circles around it like a clock. That image is wrong, and it's been wrong the whole time. The Sun isn't stationary. It wobbles. Every planet in the solar system tugs on it gravitationally, and the biggest tuggers are Jupiter and Saturn. When those two gas giants line up, their combined gravity is strong enough to pull the Sun measurably off the system's center of mass. The Sun actually loops and wobbles in a small, complicated path as it sits at the heart of the solar system. It's less like a fixed anchor and more like the center of a spinning top that's just slightly off balance. That wobble isn't just a curiosity, it echoes into something much bigger. Over thousands of years, the combined gravitational nudges from Jupiter and Saturn subtly reshape Earth's orbit and the tilt of its axis. These long, slow changes are called Milankovitch cycles, named after the Serbian scientist Milutin Milanković, who worked out the math in the early 20th century. One of the components is the tilt of Earth's axis itself, which doesn't stay locked at 23.5 degrees. It drifts between about 22.1 and 24.5 degrees over a cycle lasting roughly 41,000 years. A few degrees might not sound like much, but it's enough to change how much sunlight hits the poles versus the equator, and over tens of thousands of years. That's enough to tip the planet into or out of an ice age. Geological evidence layers in ocean sediment, ice cores pulled from Antarctica, lines up with these cycles almost like a metronome. It's one of the best documented links between celestial mechanics and the literal shape of Earth's climate history. Though scientists are quick to point out that human-driven climate change is now happening on a timescale so much faster than these natural cycles that it's currently overriding them entirely. So Earth doesn't just orbit the Sun, the whole system flexes and shifts as it goes. But zoom out further, and you find out the Sun isn't just wobbling in place. It's moving too. All of it, the Sun, The planets. Everything gravitationally bound to our star is on a journey around the center of the Milky Way. The Milky Way is enormous, almost beyond comprehension. It stretches somewhere over 100,000 light-years across, packed with a few 100 billion stars, along with gas, dust, and an amount of dark matter that outweighs all the visible stuff combined. Our solar system sits inside one of the galaxy's spiral arms, sometimes called the Orion Arm, or the Orion Spur, a relatively minor structure compared to the grand spiral arms like Sagittarius or Perseus. We're about 25,000 light-years from the galactic center, roughly 2/3 of the way out from the middle to the edge, and we are moving. The Sun orbits the galactic center at a staggering speed somewhere around 143 miles per second, which works out to more than 500,000 miles per hour. At that pace, it still takes somewhere between 225 and 250 million years to complete a single orbit around the galaxy. Astronomers call that one trip a galactic year. Here's a number that tends to stop people in their tracks. The last time our solar system was in its current position relative to the galactic center, dinosaurs hadn't evolved yet. The very first galactic year of Earth's existence hasn't even finished. We're only on lap number 20 or so since the planet formed 4.5 billion years ago. What determines that speed? Mostly it comes down to gravity and mass distribution. Stars closer to the galactic center feel a stronger gravitational pull from the dense concentration of mass there, so they move faster in their orbits, the same way Mercury zips around the Sun faster than Neptune does out at the edge of the solar system. To actually measure the Sun's true motion, astronomers look at very young stars, ones that have barely had time to drift from their birthplace, and average out their movements to establish a local standard of rest. Compared to that baseline, the Sun has its own small extra drift, sometimes called its peculiar velocity, roughly 9 miles per second toward the constellation Cygnus, about 5 miles per second in toward the galactic center, and a few miles per second up out of the galactic plane. None of these numbers are treated as final. Every few years, missions like the European Space Agency's Gaia spacecraft, which has spent over a decade mapping the precise positions and motions of more than 1 billion stars, refine them further. And that up out of the galactic plane detail matters more than it sounds like it should. The Sun's orbit isn't flat. It bobs up and down through the galactic disk like a horse on a carousel, oscillating above and below the plane roughly once every 30 to 70 million years. Depending on which study you look at, the exact period is still debated, because it depends on assumptions about how much unseen mass, dark matter included, is distributed through the disk. We're currently sitting a modest distance above the galactic midplane, drifting upward, and in a few million years the Sun will reach the top of that arc before gravity pulls it back down and it swings through the plane again. That bobbing motion has led to one of the more genuinely debated ideas in astronomy, the Shiva hypothesis, proposed by paleontologist Michael Rampino in the 1980s. The idea is that each time the solar system crosses through the crowded galactic plane or passes closer to a spiral arm, it runs into a denser environment, more gas, more dust, more nearby stars and their radiation, and a higher chance of gravitational encounters that could nudge a comet out of the Oort cloud and send it plunging toward the inner solar system. Rampino and others have pointed to a rough periodicity in Earth's mass extinction events in the fossil record and asked whether it lines up with these galactic plane crossings. It's a compelling pattern. It's also far from settled science. The statistical case is contested. The extinction record itself is messy and incomplete, and plenty of researchers argue the correlation is weaker than it first appears. But it's a legitimate, still open question in astrophysics, not settled either way, one of the rare cases where cosmic motion and the history of life on Earth might genuinely be connected. There's another layer to this too: density waves. As the Milky Way rotates, its spiral arms aren't fixed structures made of the same stars forever, they're more like traffic jams. Stars and gas clouds move into a spiral arm, slow down as they pass through the denser region, and then speed back up as they exit, the same way cars bunch up approaching a slowdown on a highway and then spread back out. As our solar system passes in and out of these spiral arm traffic jams, it may pass through regions of higher cosmic ray density, and some researchers have proposed that could have subtle effects on atmospheric chemistry and even genetic mutation rates over deep time. It's a fascinating hypothesis. But like the Shiva hypothesis, it's exactly that, a hypothesis, still being tested against a fossil and geological record that's difficult to read with total precision. Astronomers track all of this motion using a concept called proper motion, the apparent drift of a star across the sky over months, years, or centuries, caused by its real motion through space relative to us. Stars that seem fixed in the constellations you recognize are not fixed at all. They're just far enough away and moving slowly enough across our line of sight that the drift is imperceptible within a single human lifetime. Give it 50,000 years though, and the Big Dipper won't look anything like the Big Dipper anymore. Some of its stars will have drifted enough to completely change the shape of the constellation. There's also parallax, the tiny apparent shift in a nearby star's position when viewed from opposite sides of Earth's orbit, 6 months apart. It's the same effect as holding your finger up and closing one eye, then the other, and watching your finger jump against the background. Astronomers use parallax as one of the most reliable tools for measuring distances to nearby stars. And it only works because Earth itself is moving without that yearly orbital baseline. The technique wouldn't exist at all. So far, we've climbed from Earth's rotation to its orbit, to the Sun's journey around the galaxy. But the Milky Way itself isn't sitting still either. Our galaxy is being pulled by the gravity of everything around it, and one of the most dramatic examples is right next door. The Andromeda Galaxy, our closest large galactic neighbor, sitting about 2.5 million light-years away. The Milky Way and Andromeda are moving toward each other, currently closing the distance at roughly 68 miles per second. On a cosmic timescale, that's a collision course current estimates suggest the two galaxies will begin merging in a few billion years. A slow, spectacular, and genuinely inevitable event that will completely reshape both galaxies over hundreds of millions of years, though it poses essentially no direct danger to any individual star system, since galaxies are so mostly empty that stars almost never actually collide. But the Milky Way and Andromeda aren't just dancing with each other in isolation. They're both part of a larger cluster called the Local Group, which includes more than 50 smaller galaxies bound together by mutual gravity. And the Local Group itself is being pulled towards something far stranger, a massive concentration of gravity astronomers called the Great Attractor, sitting roughly 150 to 250 million light-years away, in a direction largely obscured from our view by the disk of our own galaxy, in what astronomers nickname the zone of avoidance. We can't see directly through that region because it's packed with our own galaxy's gas and dust, but its gravitational influence is unmistakable. It's pulling entire galaxy clusters, ours included, toward it at somewhere around 370 miles per second. And in recent decades, astronomers have found the Great Attractor may itself be just a smaller feature within an even larger structure called the Shapley supercluster, one of the most massive concentrations of galaxies known in the observable universe. And underneath all of that, the rotation, the orbit, the galactic journey, the pull toward the Great Attractor, there's one more layer, the biggest one of all. The universe itself is expanding. This isn't galaxies moving through static space the way a ship moves through open ocean. It's space itself stretching, carrying galaxies apart from each other as it grows. a discovery that traces back to Edwin Hubble's observations in the 1920s, when he found that nearly every distant galaxy he measured was redshifted, meaning it was receding from us, and the farther away a galaxy was, the faster it appeared to be moving. That relationship, now called Hubble's law, was the first solid evidence that the universe isn't static. It has a history, it had a beginning, and it's still growing. Given all of that layered motion spin, orbit, galactic rotation, the pull toward Andromeda, the pull toward the Great Attractor, and the expansion of space itself, how do you even measure a single, honest speed for how fast we're moving through the universe? Scientists found an answer in the faint afterglow of the Big Bang itself, the cosmic microwave background radiation. The residual heat left over from when the universe was only about 380,000 years old and first became transparent to light. That radiation fills the entire sky, and it's remarkably uniform in every direction, but not perfectly uniform. There's a tiny variation, a dipole, where the radiation appears very slightly hotter in one direction and very slightly cooler in the opposite direction. That dipole isn't a flaw in the data. It's caused by our own motion. Because we're moving through space, the cosmic microwave background gets slightly blue-shifted and therefore appears warmer in the direction we're heading, and slightly redshifted, appearing cooler in the direction we're leaving, behind the exact same Doppler effect that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it drives away. By measuring the size of that temperature dipole with extraordinary precision, missions like NASA's MAP satellite and the European Space Agency's Planck spacecraft have pinned down our total velocity relative to this ancient light, somewhere around 370 miles per second, or roughly 1.3 million miles per hour, relative to the cosmic microwave background as a whole. Let that sit for a second, because it's the closest thing physics gives us to an honest answer for how fast are we really going. Not fast relative to the sun, not fast relative to the galaxy, fast relative to the oldest light in the universe, the closest thing we have to a fixed backdrop against which everything else can be measured. Which brings us back to where we started, standing on solid ground, feeling like nothing around us is moving at all. And in a strange way, that stillness was never a mistake. Galileo was right, there's no single privileged frame of reference in the universe, no cosmic center you can stand at and call truly stationary. Every motion we've walked through tonight, the spin, the orbit, the wobble, the galactic sweep, the pull toward Andromeda, the pull toward the Great Attractor, the expansion of the universe itself is only meaningful relative to something else. Stack them all together, correctly, accounting for direction and cancellation, and you get a real number, Earth's true motion relative to the cosmic microwave background. Somewhere in the neighborhood of that 370 miles per second figure. It's not simply the sum of every speed we mentioned, because motion in physics isn't additive that way, it's the net result of all those velocities layered on top of each other in three-dimensional space. What's left when you actually sit with all of this isn't dizziness. It's something closer to vertigo of a better kind, the realization that stillness was always an illusion, and that the ground under your feet has been part of one continuous, uninterrupted journey since before there were feet to stand on it. You're not just living on a planet. You're living on a planet that's spinning, orbiting, wobbling, racing around a galactic center, drifting toward a neighboring galaxy, falling toward a gravitational anomaly we still can't fully explain, all while the universe itself keeps expanding around every part of that journey. And somehow, from inside all of that motion, it feels like nothing is moving at all. Maybe that's the most human thing about it, that we built an entire understanding of stillness, of home, on top of a planet that has never once stopped moving. Thanks for watching, and I'll see you in the next one.